All right, great. Hey everyone, thanks for staying to the last talk today. My name is Tony Gargano. I'm a postdoc at the LPI and NASA JSC, and thanks Steve for setting me up really well for the background here. It makes my life much easier. So this is some conceptual work that Aaron Bell and I have been working on for the past few months, and it's just now starting up, as well as my collaborators at NASA JSC. And here we're considering how the electronic mass balance should be considered in terms of how outgassing and ingassing behaves in lunar pyroclastic glasses, but this is also applicable to many other scenarios as well. So that works. Awesome. All right, so like I said, Steve set us up really well here for how the system works here. Now, I used to think, and I still kind of think, that these lunar pyroclastic glasses are some of the most extensively degassed materials on the moon. And it's because the conditions they erupt in. These things erupt very hot, and within the volcanic conduit, we need to have these high gas to melt ratios just to fragment these materials and exhume them as well. So we have this system of high melt eruption temperatures. These things have a lot of gas around them, and importantly, they have a large change in pressure during their exhumation and cooling path in the plume. And this kind of tends towards the idea of these things being extremely degassed. Now, on the image on the bottom left here, I'm showing you the orange and black glasses. In this work, we're looking specifically at the black glasses here. Their initial melt comps are probably very similar to the orange glasses. Simply, their cooling path is much more slow, meaning they crystallize in the plume. And we're going to exploit that behavior in our work here to understand whether or not the redox conditions are changing as these beads cool and in and out gas in the plume. All right, so ironically enough, I think the gassing processes are best understood here in terms of sulfur isotopes. This is a plot on the bottom right showing you some lunar volcanic materials where we're showing the sulfur isotope fractionation as a function of sulfur loss. And specifically in the case of these pyroclastic glasses here, these seem to be the most degassed materials, but importantly, they're degassing under equilibrium conditions, meaning that they're maintaining their equilibrium vapor pressures throughout their loss of sulfur and cooling. But this process is not unidirectional, as Steve just mentioned here. The outgassing process is also buffered by some amount of ingassing as well. So evidently, we have some amount of buffering that's occurring during this devolatilization process. So really, my goals here are to better understand the overarching controls for elemental volatility and whether redox influences how volatiles are lost or gained, and specifically the kinetics of how this rate changes during this condition. So we're looking at the black glasses again as a conceptual idea to test this idea. And really what I convey here is that in terms of how outgassing behaves here, if we look at the simply sulfur degassing equilibria here, we can see how FO2 influences the efficiency of this degassing process here. The plot on the right is showing you the same system here, where a high FeO bearing melt, the equilibrium vapor pressure of sulfur is a function of both the FO2 and the sulfur content here. I think this behavior, this Hindrian behavior, where the volatility is proportional to the concentration, is not considered very much. But in this system here, where these glasses are losing sulfur, potentially being reduced, we're basically tending towards equilibrium constantly as we're going towards lower FO2 and losing sulfur contents. Let's see here. So yeah, I think these two processes together in terms of the loss of volatiles and the redox state changes tend towards explaining why many degassing materials tend towards equilibrium, even though they're losing a lot of volatiles. All right, so in terms of how we're conceptualizing this, we're saying a simple electronic mass balance of a orange glass composition as it loses volatiles. So in this case here, I'm comparing and contrasting how sulfur and sodium are contrasting in this way. So if you compare simply the redox reaction of how you lose volatiles from the species in the melt, for sulfur, it's dissolved with sulfide. For sodium, it's an oxide. So we need to oxidize our sulfide to sulfur in order to lose it as a gas phase, and conversely for sodium in this case. So we can see here that the electronic mass balance can be maintained if these things are lost together here, but this must be balanced in some way. All right, so what we're doing here is that we're using polyvalent liquid trace elements as a first order test whether or not this matters at all, or if this process occurs. So in this case, looking at vanadium, chrome, and titanium here, we're going to begin with vanadium here because vanadium its partitioning behavior is very sensitive to redox state. So on the left here, I'm showing you how the vanadium olivine melt KD changes as a function of FO2 here. And on the right, we're showing you an image of these black glasses here. And simply speaking here, we'd expect to see a change in the vanadium partitioning and the olivine as a function of the redox state, as if these glass beads do in fact change redox state or are buffered the entire time. So as Steve mentioned earlier here, these materials are kind of a natural Monte Carlo simulation. They experience different trajectories, different paths. So we expect to see a large variation here depending upon what occurs. But really, we're going to exploit this behavior first and foremost to see if it matters here. And likewise, we'll see how the KD changes as whether or not reduction or oxidation controls drives the bus here. All right. And really, my main interest here in tying this together in terms of both the moon and also the early solar system too is understanding are volatile elements operating the buffer melt redox state. Many volatile elements have high diffusion rates. So in terms of buffering redox state, these make the most sense in terms of making sure things are balanced the entire time. So in terms of understanding both how melt is buffered, we need to consider how loss at in-gassing behaves and which one is controlling the system here. And ultimately, this also tells us towards the chemical kinetics of the rate of loss. And this is the necessary information to interpret some of the volatile element stable isotope data being generated these days. All right, so stay tuned for updates. We're starting on this work doing some SIMS analyses of vanadium pretty soon here. And look forward to sharing it at LPSC next year. And please reach out if you have any questions and look forward to questions.